If you know anything about digital photography, you've definitely heard of RAW files, where a camera stores unprocessed data straight from the sensor. You know, I'm something of a photographer myself, and I always shoot RAW. If I'm capturing some information, I want to possess all of it. I don't want any compression algorithm to take it from me for the sake of saving some disk space. But I never actually gave much thought to what exactly the data I'm holding onto is. What kind of information does the camera write into these files? In what format? And what processing is required before the image can be displayed or printed, and so on. And instead of reading articles or watching videos on the topic, I decided to just dissect a RAW file myself to see what's inside. Join me on this little experiment, but first I need to take some samples. Now that I have some samples, let's take a look at what's inside. Apart from the sensor data, RAW files also contain a lot of metadata, but I'm interested only in sensor data itself. DC-RAW helps me to extract this data to a PGM file, a simple format that is easy to read and work with in a program. I'm using Rust to write a program that reads these files and outputs an image as a ping. The header of the PGM file indicates that it contains an image with dimensions of 6024 by 4020 pixels, and the maximum value for each pixel is 65,535. This means that each pixel occupies exactly 2 bytes of data in the file. In the standard RGB model, creating a color requires 3 components: red, green, and blue. Most consumer-level displays support 8-bit color depth, meaning we need 1 byte for each component or 3 bytes for every pixel. However, it seems there isn't enough information in the file to create a full color image. The thing is, there is no actual color information in raw pixels. Each photosite on the sensor records only the intensity of the light hitting it, how dark or bright it is, but not its color. 2 bytes can encode up to 65,536 distinct values. A value of 0 represents no light, or pure black color, and 65,535 is the sensor's maximum capacity, or pure white color, with 65,534 shades of gray in between. It's interesting how we can end up with a full color image even though the raw data contains no color information. In the standard RGB model, using the same value for all 3 channels produces a shade of gray. This means that I can simply use the value from the raw file. With 8-bit color depth, each channel only provides 256 gradations. This means I'll need to compress the entire range of 65,536 values from the raw file down to just 256. Each group of 256 distinct values from the original data will be represented by a single gradation, which is quite a dramatic reduction if you ask me. Well, this is something. It does look like a black and white version of the picture I took. I'd say this is the closest we can get to a straight out of camera image. Let's zoom in to examine individual pixels. You'll notice a distinct pattern. This pattern exists because the light passes through a grid of color filters before reaching the sensor. This grid is called color filter array, and the specific pattern used by my camera known as Bayer filter. Each photosite has its own red, green, or blue filter in front of it, which means it only captures the intensity of that part of the light spectrum. So it turns out each pixel does have some color information after all. The catch is that each pixel only captures one part of the spectrum, essentially just one channel of the RGB model. To create a true color image, we need all 3 channels for every pixel. The solution is to borrow color information from neighboring pixels that capture the missing parts of the spectrum. Let's see how the resulting image looks now. It does have some color, but it still doesn't come anywhere close to the JPEG produced by the same camera. The most obvious issue is that it's very dark. And the issue comes down to our perception. While the sensor captures light intensity in a linear way, meaning a photosite receiving twice as much light will record a value twice as large, our eyes, or rather our brain, don't work like that. Our perception of brightness isn't linear. Something twice as bright doesn't appear twice as bright to us. Instead, the relationship is closer to a curve, where changes in darker tones are more noticeable than in brighter ones. There's a lot of science behind this, but the short version is that we need to adjust the raw values to compensate. This adjustment, often called gamma correction, increases the brightness differences in darker pixels, while reducing them in brighter ones. Let's implement it in the code. The brightness has improved a lot, but the image still has plenty of issues. There's more work to be done before it even looks decent, let alone ready for artistic edits. But I'll stop here for now. This experiment gave me the answers I was looking for, and helped me understand not just what's happening inside my camera, but also why and how the software processes the raw files to create the final image. Before this, I didn't really understand how raw the raw files are. In theory, all these basic adjustments could be done in the hardware and stored in a lossless file. But having access to the original data straight from the camera sensor means we can tweak, override, and potentially improve these processes ourselves. If I only had a JPEG instead of a RAW file, all these adjustments would be already baked into the file, leaving me with little to no room for improvement. For example, I can still take a RAW file from my very first DSLR and reduce noise using modern algorithms that weren't available back then. This was a really interesting experiment. Sure, I could have learned this by reading articles or watching videos, but hands-on experience is so much more fun. I hope you learned something along the way too. Thanks for watching, and I'll see you in the next video. Bye!